Hi, good afternoon. Thank you all for joining our webinar for the month of June. So this is the third one in our series that we are conducting. So I will invite Mr. Jayant Pereira to start the remarks. Thank you, sir.
Thank you so much. As the president of the Chamber of Construction in Sri Lanka, it is my pleasure to welcome you all to this critical webinar titled Low Carbon Concrete, Alternatives and Sustainable Building Materials. As we navigate an area where our nation confronts mounting challenges, the urgency to explore sustainable building materials has never been more appropriate. Today, we are excited to discuss alternative building materials, an approach that saves the benefits of our planet. These solutions are becoming more efficient, more accessible, and most importantly, more cost-effective in the long run. By embracing them, we can reduce our dependence on and create a cleaner environment for future generations. Today, we are honored to host a distinguished expert, Professor Priyan Mendis, Senior Professor in Engineering at the University of Melbourne and Founder Chairman of the Green Building Council of Sri Lanka. Bringing a wealth of knowledge and diverse perspectives on alternative sustainable building materials, who will share invaluable insights that illuminate the vast opportunities and inheritance challenges we face in using the appropriate materials. Our discussion will delve into critical topics, including harnessing our country's available sustainable materials, enhancing use of same, and addressing vulnerability posed by climate change. This dialogue is designed to empower us as we strive to build a more resilient, sustainable, and affordable future for all. I strongly encourage each of you to immerse yourselves in this session, ask questions, share your thoughts, and collaboratively explore innovative solutions. Together, we can contribute significantly to creating a greener and more sustainable Sri Lanka. Thank you for being here, and let us embark on what promises to be a productive and inspiring discussion. Thank you very much.
So thank you very much, and welcome all. I think I can see a bit of a large gathering here already. So thank you very much for joining us today. First of all, thank you to Architect Jayant Pereira, my good friend also, and also present chairman of the Green Building Council, and also the chairman of the Chamber of Construction Industries. So CCI for basically inviting me for the CCI. I think in this series could be the first one in this series, inviting me to join. And although I had to be today away from Colombo, I'm joining from one of the most beautiful cities in Sri Lanka, Kandy. Today, I had a very good session at Peradeniya University today, Dean and the head of department and others today. So a very productive session. So I'm joining from Kandy. So I'm sure I really won't have much interference, just joining away from my normal home in Colombo. So coming back to a topic which is very timely, and again, a congratulations to CCI for thinking about these topics and really bringing closer to the construction industry, because we can talk about in different forums, but end of the day, it is the construction industry which has to really change and also embrace these ideas. So in that way, this is ideal forum to really talk about this topic. And so today I was invited to talk about low carbon concrete and sustainable building materials, which Architect Jayant Pereira rightly kindly pointed out that the comments in the Green Building Council of Sri Lanka to many other sustainable initiatives that I've been involved with in Sri Lanka and many other places. Australia had some leadership. I probably have the leadership in low carbon concrete in Australia, and of course I attend other world level forums as well. So the knowledge I'm going to really talk about this topic is the state of the state of the art, or what is happening in the world scene. So not just confined to one region. So my beginnings in concrete, I just want to give a very quick introduction to concrete. So and I will also only take the time that I've been allocated for this 35 minutes or whatever time that I'm allocated. And I know there's a Q&A session also later on. So I will only take that time and try and finish the time that given to me. So my on the left-hand side, the top where I entered, how I entered the concrete industry after my PhDs, and when I was working as the structural engineer and also project engineer for this building on the left-hand side, Telecom Corporate Building, is where I started, in fact, using very like high-strength concrete. First time in Australia, I used high-strength concrete. One on the right-hand side is the one in at the Telecom Corporate Building where I was a project engineer. And so in that one, I had a chance to introduce 65 MPa concrete. Even at that time, we didn't know enough about anything about very low carbon concrete, but I tried my best to be sustainable. Sustainable name we all knew, but I think we have gone a lot far now, a lot further now, which I will talk today. One on the left-hand side is Petrus Tower. That's where, when I was studying there, I had one of the best concrete technologies in the world. I need to really, one of my mentors is Ken Day, who has visited Sri Lanka. And he really, in fact, got me involved in the foundations of the Petronas Twin Towers. Even at that time, I was studying at Monash. And so with that introduction, I learned a lot from him working on that, the foundation structure. And since then, I, in fact, worked closely with him. And also, then I was chaired the High Performance Concrete International Committee of the ACI, American Concrete Institute. So he was with me all the time. And I need to acknowledge him because he taught me a lot on concrete technology. And there are other mentors for me, like Professor Mehta, again, is like that. There are few people I can name, even Neville I have met, and he's given me advice at that time. So one of the leaders I had a chance to really associate leaders. And coming back, this recognition for concrete industry, the service to the this outstanding service to the concrete, that's the highest award given by the Concrete Institute of Australia to admitted to the honorary membership. 2017, that's the president of the CIA, or Concrete Institute of Australia, so giving me that award in 2017. So that is the highest recognition, as I said, in Australia. So I'm very that in the service to the industry, basically. So then the opportunity to work on the columns of the Burj Khalifa, the tallest building in the world. I learned a lot by even attending workshops, and my work is confined to the design in the concrete, high-strength concrete columns, the rules, and using them. So it's a landmark building that's still the tallest in the world, 824 meters, Burj Khalifa. So this also, if I have time and questions, we'll talk about not the challenges, the Burj Khalifa, building the Burj Khalifa. And again, as I said, I'm only was involved in the columns, but I got to know a lot of information through workshops and other communication. Then the Shanghai Tower working, I'm saying these examples because they are a sustainable high performance concrete type of examples. Even at that time when the landmark structures being built, Shanghai Tower, the second tallest building in the world still, the 632 meters tall. And it's a unique structure. I will not talk about in my tall building lectures. I've talked about all the really other features of this, which is a unique building. And that's the building with right now with different floors, zones and all that. So in this one, my involvement was with the Victorian government nominated me because there was a formal project with Shanghai Construction Corporation to help them with the high performance sustainable concrete. So to really this project, that's Mr. Gong, my friend, who's a project director of this project, lead of the project. And this is when the concrete was topped up 506.9. The pumping record was broken in the Shanghai Tower. I happened to be there that day just visiting because I was part of that right now from the Victorian side, Australia side. And yeah, so I think these are all learning for me on the practical side of it. I can do many things in the lab, but getting this practical exposure is where I really value not only Australia and other countries. I'm like now working here in Sri Lanka. Even I have to acknowledge Mr. Shomal Fernando. Working with him, I have been really, we have made a lot of innovations in Sri Lankan concrete scene as well. So coming back to my talk will be introduction, the low carbon concrete, and then some applications in sustainable materials, and then I will be touching on again where we are going the next decade towards net zero, which is coming up not too far. So we had to really do something now. That's why CCI bravely like not get into these sort of areas. So in terms of continuing on the outline, we are again we have materials towards there's new opportunities, research directions, structural and materials engineering, or not only for the researchers, for the construction whole industry. There are new opportunities created because we are very important. Even if we want to, no one can ignore us, the construction industry, because we are the ones who would be really one of the most important moving towards net zero. So again, we had to push the lab to field type of applications. That's where I'm taking my large research group in Australia towards that lab to field. I'm not really, there are academics also joining a lab. I have to say this, we can do many things in the lab now. So the field commercial applications is a difficulty. That's where I am actually taking my group, which is a bit of lacking in that gap between lab to the real field is there at the moment, working with the industry. So that's where I've taken my group. So we need to do a lot of work on standards and specifications coming in a job. We need to do something on material structures, how to really looking at the materials to the structural performance, and how we really reverse engineering or reverse work on structures, and then looking at the performance and then designing the materials. These sort of gaps are there. We need to do a lot of work. And again, today I will not talk too much, but I want to mention I'm doing a lot of work on what's called calcined clay. We are even there's waste material, and today only can only talk for one slide on that. But it's an area where like now I've got to do a lot of work now. Sri Lanka also has a lot of clay, so let's see where we can take forward all that. We have been using clay bricks, so why not using for concretes and all that? I'll make some comments like that. Concrete and so on, we can do anything. The second slide show that pushing the boundaries, you can do anything with concrete. It need not be just straight slabs. That's in a structure, Portugal. Third one is where we are heading. Again, I will not talk today. Is more of the infield robotics and infield like and then doing the 3D printing and all that in the lab. That's some interest. Like now my group has some interest in that as well. Coming back to, let's not spend time on, we all know about this, why we are doing it. The carbon dioxide, we are doing it for the future generations. So we have a very dangerous emission levels still. So we need to do something. And we know this video works like now we see the temperature changes from 1800s to where we are heading. So climate change is real now. We know that at that time when we started a lot of things, like no people didn't believe, even America more than 50% didn't believe in climate change. Now almost everyone believes climate change now. So that way, at least positively, people are thinking that climate change is happening everywhere in the world. And we know that this is real. The temperature changes until 2022. You saw how we started in 1800s and now where our temperatures are. We are at a very dangerous levels of temperature levels. Unless we do something, we can't this impact will continue, and so it's really dangerous. Earth will continue to warm, and the effect will be really serious and bringing consequences. So we need to do something for the next generation. So let's not talk too much on the COP26. We all know about UN SDG goals, Sustainable Development Goals, and we had to reach the carbon neutrality by 2015. We are behind, and the recent UN report says we will reach at 2 degrees at least. So we are behind. We were, so they, in fact, COP26 said 1.5, but we will reach about 2 degrees. So it's still at dangerous level. So we need to do something. And here, this is an important statement. Construction industries uses about 1/3 of the emissions of the world, and half of those comes from 2 materials, steel and concrete. So mainly concrete, we use concrete is one of the main materials which brings these carbon emissions. So we use 1/2 ton of cement per year for every person alive in the world, whether we like it or not. Everyone without knowing, like 1/2 ton of cement, every person is using. So we need to do something. So I will not talk about background too much. This is a very busy slide, but no need to read from this. What this says is 1 ton of cement really emits about 1 ton of carbon dioxide. So similarly, 1 ton of concrete emits about 0.9 tons of CO2. Cement produces about 3 billion tons of greenhouse gas emissions, so which is about 8% of the world total. So it's really, we are at a dangerous level. The reason for that is this one here. So with the emissions, so limestone in the cement production process, those now have access to these days. Now you have, no, I didn't have that chance when I was studying, but all the younger people have the chance about the Googles and now even ChatGPTs or DeepSeek or something. But to really, you can put these words and then get a lot of information. But with the limestone, the reason is that cement production, calcium carbonate is really heated around 1500 in the cement process, the cement production process. So to convert into lime, CaO, that emits the CO2 when the CaCO3, calcium carbonate limestone, is heated at very large temperatures. Again, I will not go through the cement manufacturing process. It's really going through clay to limestone to rotary kiln. That's where the damage happens, and 1500s and all that. And then going through the cement manufacturing process that you can read from the web. All this. So what can we do? Basically, we need to really we need to it's an idealized reduction rate for embodied carbon in a zero carbon future. In this one, the y-axis is on the embodied carbon, and the year is on the x-axis. So this is the critical period for change. We know we will reach the net zero we want to reach in 2050, but we can't wait until that time. So the most critical period is until about 2035. Next 10 years is the most, next decade is the next, the most critical decade. So we all have a responsibility. We can't wait until later on. Now it's already late doing things. So let's see, as a world, I'm not saying just Sri Lanka, whole world, we need to take some urgent other action. Things are happening, started to happen, but we need more work to be done. So let's go to basics. I start with the basics, where let's go back and work on the basics to make it sustainable. We have cement. So let's see, cement is the problem. And when we water sand and gravel, we can make it a bit more, we can think about their fillers, but we can think about really making them sustainable as well. So we can go back to basics. I'm not going to teach the basics of concrete today, but with this limited time, but we can really see where are the cement, water, sand, and gravel. So, and then paste plus a pillar is the concrete. So we will really go back to this and do the fundamentals. This is more not to worry too much. This graph, the reason I'm saying this graph is the reason I'm showing this is how the concrete was really started. The y-axis is the specific surface area, or particle size is on the x-axis. I'm not going to talk too much technical today, but this is a very important graph for anyone. That is where we started with the large particle sizes. We are reducing the particle size and going to the left a lot more. We are increasing the specific surface area. And we have gone through this journey of conventional concrete. Then we went to high performance, high strength concrete. Now we are talking about nano engineered concrete, and to make it even more sustainable. So these are the things that we are going to do in the next few years. We will be doing, this is where I did lots of work, including change in the Australian code. I took a leading role to the 120 MPa. We are probably one of the highest in a systematic way in the world, about 120 MPa. I was leading that way in Australia. And we have done a lot of good work in high strength concrete in some projects in Sri Lanka as well. The stress is on the y-axis and strain on the x-axis. We can see we can reach very high strengths, but it's brittle. When it reaches the high strength, it's brittle. So to have sustainable concrete, low carbon concrete, high strength also is quite important. By having the high strengths, you can reduce the sizes of the members, not just the materials. We need to work on the sizes of the members as well. So high strength is obviously a good choice to make it low carbon, reducing the sizes of the components and the members of a building or other infrastructure. So getting to high strength, the problem is it becomes brittle, because we can see the straight line. I will not go into all basics. It becomes brittle. For low strength concrete, it's very ductile. It's like parabolic curve. But with the high strength, it's like go straight, and then very brittle it fails. That's where my work on the Burj Khalifa is already in this book. I don't know whether it can be bought now. I wrote this in 2001, and I think it was very popular. I didn't get much money from the publishers, but I know it was many people bought this one. Anyway, coming back to the high performance materials for the future, and the lightweight, again the high strength, lightweight, the high performance material for the future. We need lightweight materials, high strength materials. We need durable materials. We need affordable materials. We need again the environmental friendly, low carbon, sustainable materials. So we need to look at all that. So we had to work from backwards from the performance. So I'll give some solutions in the next few slides as well, where we could really go through. And in future talks, I can talk in a bit more detail of some of these topics. So it is really how to decarbonize the construction industry. Is really we have to look at zero carbon or low carbon materials development. That's why we all are here today. And we need to really develop some evidence base. When you develop new materials, field applications, we need to really have a evidence base. So that evidence base is really quite important. We need to change the performance base, standards and the specifications. And so we need to bring all that together to really make it successful, all that together. We can do anything, developing materials. We need to really confirm that they work, and especially longer term as well, not the short term. And then we need to change the standards and specifications. We need to really make sure the people who are doing the standards and also specifications. That's what I'm doing in Australia. I'm leading a concrete code. There's a subgroup also using like these low carbon materials. So we are trying to encourage them in the industry. And the specifications, we want to really change the specifications. We have drivers and barriers. The policies are the drivers. We need to really look at net zero targets. We all have to really look at the end of life considerations as well. And I will not go through, but we need to do what's called life cycle analysis, whole life of the structure, building or infrastructure. Australia has developed carbon credit units, all countries. I'm sure it'll come to Sri Lanka as well. So carbon credits, it's really valuable. It's dollars and rupees type of value. So some incentives for really using low carbon materials. In Australia, it's compulsory to use low carbon materials. Industry is really the clients and all that are really have to comply with the rules. So I'm sure in Sri Lanka also with this will be introduced. It make it compulsory to use low carbon materials. So that's this webinar's time, really the good timing towards all that. So barriers is the procurement. How to procure the material, and this is a problem for construction industry. Processing cost, there's a processing cost. We need to look at the mechanical properties, the short-term properties. We need to look at the durability, long-term properties, field applications, as I said, and the standards and specifications. So there are barriers. We all have to work together, not just people who are developing materials, the designing components, but construction industry as a whole had to work to achieve this. So how can we reduce or remove carbon emissions? So to really do that, we need to using less cement. Obviously, if cement is the polluter, we need to use less cement. And we have to increase the recycling rate. We had to use recycled concrete. We are demolishing a lot of concrete. So why not reuse? So there are issues. I'm doing a handbook now for Australia on the recycled concrete aggregates, concrete. So really, we are encouraging higher levels of recycled concrete aggregates. At the moment, we are allowing only 30% of the recycled concrete aggregates to be used in practice. We are doing some guidelines trying to improve that recycled concrete really use in Australia. And the third one is, if I have time, I'll have a slide, but geopolymer, which is cementless concrete. We call it inorganic polymer concrete. Again, there are ways of doing it. We are using the alkali activation. Alkali activation is a key word to achieve low carbon concrete. So we're doing a lot of work, and we are also trying to develop some natural activators, not just chemical activators. So this is an area for really future for Sri Lanka as well. I try to use geopolymer concrete. I remember working with Mr. Ravi Vishankar Millennium Concrete, pouring geopolymer concrete for about probably 10, 12 years back, doing a trial. But I think since then, I'm sure it's slow in the world to really to be used. But I think in Australia, we just finished a handbook, PS199. So similarly, we can bring that to Sri Lanka as a bit more. So again, the fourth one, which is quite important, reduce the clinker by using supplementary cementitious materials. I will talk about that bit more very quickly on slides. So we need to really add these supplementary cementitious material, which to get to the low carbon concrete waste materials. So what we do here, if you want a bit of background, the cement paste, we super processes are to improve the workability, just to improve the flowability of the concrete. We use that for almost every concrete now. And then we add that other material, which will really improve the properties. Silica fume example is a waste material. Let's see here. These are called pozzolanic materials, and they are natural pozzolans. Natural materials are there, fly ash, slag, silica fume, and even rice husk ash. We got a lot of rice husk. And I remember doing a pilot project on rice husk ash here long time back with another university. And we got somewhere with that. I think we need to do a bit more systematic work. At that time, when I was when we're doing that work, that encouragement wasn't there. But now with these new sustainabilities, even support in Australia and other countries a lot more interest now. So it's easy for us to do work. So workability is this is really something. It's not a lesson on concrete. We need to really, with these low carbon materials, make sure the workability is there. The reason I'm putting this slide is people have got into trouble, try to say, right, let's use some materials, low carbon, but they get into trouble with workability. The ease of placement, cohesiveness in concrete is lost. Some consistency, ability to flow is lost. So we need to carefully design the material. That's why we need experts to do that, rather than someone like we can do our own backyard concrete, whatever way, but we can't do in an important construction project. So we need to specialists to do that, engineers to architects to be involved. That's why they are construction industry people, technologies, they all have to get together and do this work. We can't just ask just an ordinary layperson to go and pour some concrete, which is maybe happening in some places. But anyway, so we need to really, let's go to the next one. So this is the fly ash. Very quickly, the coal-fired power station, Noracholi is a good example, and has fly ash, which is really a waste material. And also there's a bottom ash, which we can use. Bottom ash is not as really favorable, but it can be used. So some work, I know people have done some work on that. And so again, it can be removed as a fine dust. Fly ash is a very good material. However, in the world scene, coal-fired plants are closing. And Australia is closing very quickly. By 2030, all coal-fired plants will be closed. So we will not have any fly ash being produced in Australia. I'm sure we can't afford to do that here, Noracholi and all that will continue. However, many countries are closing coal-fired plants. So fly ash is going away. That's why we are doing work on calcined clay as a replacement. Slags. Slags are the blast furnace slags from the iron furnace. Slag is a very good material as a waste material. It's a pozzolanic. That means improve the concrete reactions. Today, I will not talk about any reactions, but it helps concrete. Other one is the microsilica. Don't read from the slides too much. Microsilica is coming from the ferroalloy industry. It's expensive. It's not produced here in Sri Lanka. So microsilica, I think, is imported. Silica fume is necessary. Microsilica is necessary to really get to very high strengths of concrete. So it's an essential component. So we need that one, the microsilica or amorphous type of silica we call it microsilica. So we need that as well as ingredient to produce high strength, low carbon type of concrete. Let's run through very quickly some other innovations that my side, the examples. Like now I'm one of the pioneers at least in Australia, using some of these materials. And we have brought that here. I show one of the examples here. So this is the metals, the steel, aluminum, copper, concrete. We have all the asphalt, pavings, timber, gypsums, roofing, bricks. Why not recycle them? We are recovering them and recover and recycle. We didn't have this push before, but now with this new low carbon sustainable materials side, we need to recycle all sort of materials, and that's something researchers do that, and the other R&D work supported by the industry. Tiles, tires, solar panel. Again, in this case, there are certain materials. Now, this is a diagram that one of the applications we did in Sri Lanka. I'll show you the structure is in one of the. It comes later on, so I'll show you there. Anyway, so I'll skip that one. But these are so lab to field is a key one. Let's try out certain things here also. The glass in here in a large infrastructure project, my group used the glass waste for the first time in Australia for a large project, glass in concrete. There are other challenges happens. I will not spend time today. I don't have time to talk too much, but it was the glass was hitting the pumps. So it's different types of problems that we get in the lab when you go to the field. These sort of problems, that's why people are reluctant to use, but let's work together even here and try to use some of these sustainable materials. Solar panels, we are in fact now being outdated. Some of the solar panels been removed. Even here, I've seen it's happening. So where do we just throw them? We can't, in Australia, we're not allowed to throw them. We need to get the glass. There's a lot of glass in the solar panels. So I was leading this project. The Solarcrete name came from me to the company. Lexam is a company. They have a commercial plant now converting these solar panels to solar glass into, and that we can use in concrete because we are running out of sand and all that. So even that we use some waste materials. And this Lexam is a company. You can look at the Lexam website. And the other one we are doing is converting into plastic to sustainable materials, plastic sorting. I will not go through that. Even the construction products, we were using plastic products. We are now trying to use recycled plastic type of materials. So we got a robot doing that work. I will just skip that and maybe. So the robo this is still in our lab project, not in the robo. Humans, we can't do that. This accurately, we need to get these robots to do that. So we got a really full-scale facility developed. This is the application in Sri Lanka. This the CSEC headquarters we use for the bottom slab all the waste materials. When you did the for the bottom slab, the graphene oxides to plastics, rubber, which I call it the Flustaller slab. We use all sort of crushed glass from a few years back now. Bottom mesh, recycled concrete aggregates, textile here, and that slab is really doing very well. It's not without any problem. So we have done something here which no one has done in the world. Mixing all these waste materials together and putting into a real slab. So where are we forward? So in this short talk, I think I'm getting to the end of the talk by time, but we forward next decade towards a net zero system. We need new innovations. We can't just go on like this. So we have to talk about new innovation. That's where I'm working on that. We have a lot of work to do on the carbon dioxide capturing. So in the cement production plants, which is really still new to the world, in 1 or 2 places they're trying out now, we are really capturing the carbon dioxide. This captured carbon dioxide, we are going to use it in different applications, which are briefly mentioned. And so you look for this, this thing happening, that is capturing the carbon dioxide in the really from the cement production process. That will produce that is a big solution for this the problem with concrete and get into the low carbon concrete levels. Other one which really I already mentioned, the geopolymer type of technology is essential. That is with cementless concrete. So we can use the we call it precursors, different materials. We can use fly ash, slag, clay, also even rice ash, and many other materials. And with the right-hand side is alkali activators, sodium hydroxide and sodium silicate type of materials. We are using now, trying to use natural activators to these alkali activators. And then we get this what's called geopolymer concrete or inorganic polymer type of concrete. So it is really that process that we can really produce with sodium. Sorry, those who want a bit more detail, it's silicon aluminate type of processes. We go through not the usual, the calcium hydrate, CSH type of reactions in concrete. If you want to go a bit deeper, I'll leave that to another time. So other one which we are, as I mentioned, this is an innovation. Naturally, I'd give a lot of credit to Karen Scrivener in Zurich for coming up with LC3, low carbon material. I've been known for a long time, but this is something that we can do with the ordinary Portland cement, and with the fly ashes and all that, we mix it, and with the blended cement, which you already, even here you can buy the blended cements now, but blended cements, and what we're doing is adding limestone, and then with that calcinated clay. So with the calcinated clay, rather than fly ashes, we add the calcinated clay, calcined clay, which is really take the clay from the waste material, and we heat up to about 700, 800 degrees, and that gets a calcined clay. And then with limestone, so LC3 is really replacing a lot of cement in the clinker. So that way we can reduce the emissions by half or more. And then that's Anuradha, who is working very closely with me on like one of the research fellows now after very good PhD in concrete. So she's the one who's leading that work with me. So it's the magnesium-based cements there with, it's really, which is coming up. You can look for that. Today will be very brief. Magnesium-based cements, last couple of slides. Magnesium-based cements are promising low carbon alternative. You will see a lot more in the future for low carbon type of materials, the magnesium-based cements. magnesium-based cements can absorb carbon dioxide during curing. So all that the captured carbon dioxide we can use to be absorbed by this type of materials. So that will give us that full circular circle, and the carbon dioxide captured from the cement production process can be used with these sort of materials and then convert into very valuable materials. So look for these magnesium-based cements in the future. I don't think it's come here yet. These are all some early stages. That's something next decade we need to do a bit more work. I got one project or probably a couple of projects now looking at this. I'm actually not calling low carbon now. We are working on net zero concrete, but going to the zero levels. But it's probably too early. We need to start with low carbon concrete before net zeros. The other one I'm working on is that I'm already to disclose this, but even some newer rocks, even we have in Australia, olivine, which can absorb carbon dioxide. This has been ignored in the past. It's some volcanic type of rock. So we are using that to really absorb it can absorb carbon dioxide. So this is a newer type of work which we got a grant. Myself working with one of the leading professors from University of Sydney, Professor Ransi, we got a grant to work on this and looking at olivine absorbing carbon dioxide with that, and then get what's called net zero cement. So that's something that for the future I can really talk hours on these different techniques, but I will one last slide and I stop there. Recycled concrete aggregates. Another thing that we are doing is that we are passing carbon dioxide for the recycled concrete aggregates. Recycled concrete aggregates are weak because there are two layers. One is an old concrete layer, cement layer. Other one is a new cement paste layer. So there's a weak layer around the aggregates. Those who want a bit more detail, that is the weakness. That's why we can't use too much recycled concrete aggregates. So we are passing carbon dioxide through that, and that carbon dioxide will convert that layer around the aggregates to a very stiff calcium carbonate. So that carbon dioxide, captured carbon dioxide from the cement production process can be used to improve the recycled concrete aggregates. Our initial trials are showing that we can even improve and increase that percentage to about almost 100% recycled concrete aggregates can be used if you have carbonation. So that's another area which we can really see things happening in the world in the next so many years, so few years, and there'll be things. I'll keep you updated the international scene, and maybe because I give talks time to time. And then again, I want to thank the CCI for taking this initiative to really have this important topic. And but I know it's a limited time, but I think I've tried to say things, but where I can talk hours and hours. But this is a summary of where we are heading on the low carbon concrete and generally the incorporating some of the sustainable building materials.
Well, thank you very much for that amazing run through on low carbon concrete. Thank you very much. That was very knowledgeable. We will have the question and answers. Sir, would you be able to field them, which are in the chat box, please?
All right. Yeah, sure. I can approach the chat box. Yeah, I will go through that. Yeah, so I will actually maybe I think
you could take them at random if you wish.
Oh no, actually I think it's okay. I can go through the order here. So at the moment, actually we don't have many, but so I think I should be able to go through them. I know we have a limited time, but Mr. Premachandra's question on I'll read the question, and everyone has access to the chat, but I will read the question. Mr. Premachandra is asking, at the moment, demolished concrete end up as filling materials, and it is not recyclable in Sri Lanka. Do we have chemically activated blasting processes to recycle debris of concrete, like chemical blasting of rock? So in this case, it is really when I mentioned the demolished concrete, so demolition processes is a good question. So the control blasting processes had to be used Now, even if you don't use the usual the sophisticated blasting processes, it's a very good point. We can control it by having the blasting processes control in a way that it can be like we can get a lot of very good recycled concrete aggregates. That can be done, but what we are saying is not to just use the ordinary methods, and rather than using, because with chemical blasting and all that, having to separate processes. So I think that's something that actually we could really talk to the blasting experts, like how difficult it is to improve the processes. But my point is also usual blasting process that we use here in Sri Lanka is okay to demolish the concretes to a certain level. Once it's demolished, I know at least one plant that I saw in there's someone well known to me, and he said to me that he started this recycled concrete aggregates after listening to me in a talk, which I gave, I think 2020 or whatever. And he's now had a recycled concrete aggregate plant where he, in Induruwa, that he converts the ordinary, the demolished concrete, and he just process it. So you need a bit of processing. You don't need to take the cement paste out. As I said, this it's very expensive to take the cement paste out. Then of course that you can use like a normal aggregates. But rather than that, at the moment we are allowing 30%, but we can increase that percentage a lot more. Now, also I mentioned in the last slide, we can take that through a carbonation process, which will improve the paste around the aggregate. So I think that's a better way rather than trying to fiddle with the blasting methods. That's also, if possible, can be done both. So that's a good question. I think maybe we could look at the bit more input from that industry to really see what can be done in Sri Lanka. But at least one person bravely has started this, as I said, the processes. So it's happening in Sri Lanka, the recycled concrete aggregates processing, like production in some smaller scale even, is happening at the moment, which I saw a few months back. So the second question from again from Mr. Premchandra is that the structural steel produced in an elastic arc furnace emits produced in a blast furnace. It's a very, very, very good point, very good question. And so it is really something that at the moment it is I didn't have time to, so thank you for pointing that out. The steel blast furnaces, yes, the present processes are really emit some carbon. So it's really have something which it is really a carbon intensive. So we need to really use in the electric arc furnaces. There's some trial work been happening to really replace with electric arc furnaces. Yes, they are much better, but what I've been told is it won't get the same efficiency. Again, I'm not a steel production expert, but I've been speaking to people, and I have a relationship with one of the the steel blast furnace slag manufacturers in terms of they're supporting some of our work, have supported work. Not now, that project is finished on slag concrete. What they have been telling me is that one way is very expensive to change the processes. Also, they are saying that it's not as efficient as the present processes. So that's a very good point that I think we can look at electric arc furnace type of methods, because slag is used for every concrete now. Because fly ash is not encouraged much, we don't have enough fly ash now because some coal fire plants are closing. And we don't want to import in Australia because no point if you just stop the coal fire plants and they start importing. So fly ash is going away slowly, but here at least we still have the Norachuri plant, but that's probably not enough fly ash produced. So that's why we need slag now. The slag is to be in Australia. Slag has some other important properties as well. Those who are going to bit of concrete technology, slag is very close to cement. The fly ash is more aluminum silicates, silica type, but slag is a bit more calcium based, so very close to cement. So replacing by slag we can replace large percentages. We are replacing the cement to get low carbon concrete, replacing up to about 65, 70% even, because it's like cement. So that's like now one of the very briefly the answers. I hope the answers is like now the first there are a few questions, so I'll go through it bit more quicker. Mr. Jayadev is mentioning how to control the quality of these recycled materials at large scale industry requirements. So that is a very good question, because as I said from the we can do easily lab, we can get now we can select materials, all that, but get into the large scale industry requirements. That's why the recycled materials we need to really either that's why the limit of 30% the materials for the concrete, demolished concrete, the fly ashes and all that are the recycled materials are really very safe, very clean. So we can use for large percentages. Even personally, I had a PhD student who said, we're doing some work to have high volume fly ash, we can even go up to 80%. But there are other problems which I'll spend not time today, like the early strength problems and all that. So we need to really, as a team, work on it. We can't just blindly go and use this concrete. Now so it is a good question, the control, the quality of the recycled material. It's not easy with the industry requirements, but what we have done is to really bring in specifications. Actually, if you are interested, you can look at in at least Australia 3582 series, where we brought some performance requirements for the material like fly ashes, slag, silica fume, and we have done now other pozzolans where we brought calcined clay and all that in 3582.4. There are some RILEM documents as well, where in the European side you can look at as well. So there are some performance documents are helpful to the industry. It is a problem. I'm part of ISO TC71, which is really world body, like looking at standardization. In the even meetings we discuss this, but so you will see a bit more performance requirements coming from the standards, so that easy for the specifiers and for the industry to comply with these rules. So that is probably the answer, a bit more. And the next one, again, Myra is asking, how do you view the rubble of Gaza as recycled after the war ends? I don't have any idea of that one. I'm sorry, I've not done much work on that side, but my knowledge on that is not the expertise on that. Is it different to the other concretes or that? But I think it's I don't think I would probably encourage. Let's like no, let's not. We don't want anyone does not want conflicts. So let's hope to like no with the end of those conflicts rather than worrying about what is happening to the concretes. The next one is from Mr. Mohan about when you introduce such new materials, what strategies would you take to address end-use excess? That's a very very good point, because finally, as I said, we need to have evidence base. The problem we are having with new materials, even the solar panel glass, which is durable, so we don't have any problem. But some of the glass concrete we could use only for the temporary structure still. Like now, because it's still the clients, which are the government is a client in some of these large infrastructure projects. Really, they want more evidence the longer term, which we don't have all the evidence. So we need to do some. That's why we are developing some accelerated methods now. We can't wait for 20 years. Fly ash and all that we had. Malhotra had 10 years of work at that time, CanMed, to show fly ash works. So we had all that background for silica fumes. That's why slags and fly ashes and all that came to the world, which one of the people introduced here to Sri Lanka. I remember giving talks on fly ashes a long time back, so many years back. But so I was based on Malhotra's work in CanMed. But so we had the evidence, but new materials, we don't have the evidence. A very good question. We need to convince the end users or the clients and the developers that all the people who are doing specifications to include, but we are developing some accelerated methods. Already there are some accelerated durability methods. Short-term properties, no problem, we can go and confirm, but longer-term durability is the key. So there are things that we can do. I can talk about this a bit more, but it's a very good point. we need to convince, but we need some evidence base, as I said, to really convince the end users that it's not a problem. And actually, we are doing enough work also to convince them now. Again, the questions from that is on the what is the most available recyclable material in Sri Lanka to use as an alternative for low carbon initiative? That's a good question. It has to be processed. Now, obviously, the fly ash is still not actually, we have got a lot of fly ash there, and we have even bottom ash, which we can go and use that. So in Sri Lanka, this is readily available, the fly ashes and all that. There's no reason that if someone is like ready to use, convert the glass, even plastics we can use in concrete for low carbon alternatives. There are properties. At this stage, I want to say concrete is not a dumping ground for unwanted materials. It is really, once we put these materials, concrete properties improve. Even the putting plastics, we can reduce the cracking, shrinkage, crackings, and all that. It's a flexible material, so we can use that. Also, we could use things like recycle asphalts. All the roads, we are breaking so many roads, asphalts. We can go and use the asphalts and reuse them as the material, reuse them. So asking good question, what are the most available? Those are the materials that I would mention. It can be easily, but as I said, when you demolish a structure, every material we remove, think like that it can be recycled. And we can do something with that material, which we just throw it to a side somewhere before, and then we just dump them somewhere. And then, but now waste is really, we need to think about before we throw them out. And that attitudes are changing in the world. Still, certain things are difficult. Someone, like I mentioned, gypsum at the time, plasterboards or something, very hard to really recycle and reuse. What do you do with them? So, but these are the things, early stages. Another one in the construction industry, I'll just touch on them. I didn't have time to talk too much, but other one is the polystyrene. We use a lot of polystyrene, but polystyrene is not degradable. So it is a problem in the world, polystyrene. So we use a lot of polystyrene in the, or the rigiform, we call it as simple name, in the construction industry. So we are just throwing them, like how can we throw them out? And that's really pollute the environment. So, but these things are starting to be recycled. I mentioned there are lots of solar panels. Why not someone starts really recycling the solar panel glass? So let's go quickly. There are a few other questions. And it's, I think the structural steel, again, Mr. Mohan is saying about structural steel. I hope I can spend some time. Is that all right? We are going a bit over time. Is it all right? Sure, let's go. Yeah, maybe quickly I'll answer the questions. So no, thank you. There are many questions which really, that means audience is engaged. That's why there are a lot of questions asked me. So so let's try to answer all the number of questions. But with the encouraging use of structural steel is a good option. So that is correct one way. But the thing is that structural steel, to produce structural steel is again, it's carbon intensive. But the problem is now they are using this green steel. As we know, green steel is to produce structural steel. We use less energy, use renewable sources. So you get the green steel. So we can manipulate that and all that, and then have green steel. Now green steel is a big area, so which we can easily. I know it's not steel is not produced here that way, except for the doing the the steel manufacturing, the reinforcing bars and all that. So those processes are getting to be sustainable. Some of the processing done. Steel needs lots of processing. If it has to be reused, it may have to be like a process. But steel is a good material, it's a good point. So what we have to do is to have really bit less welding and all that, have bolted joints, all sort of things, so that it can be easily dismantled and removed. But that's a good point. That's something that it is a material where it is always recyclable. But only unfortunately we can't use the same members, same sizes, everything in every project. So we may have to fiddle with that. So there's a processing cost and all that when we try to reuse them. But reuse of steel is a very good point, and we should reuse as much as possible. Then the questions to, thank you, Chamodi, for answering this question. The Chamodi is taking a leading role in Green Building Council. I know doing a lot of work in this area. But the what precautions should engineers take when using LC3 in coastal or marine environments? I think some so good. I will leave that to like even I have a discussion with you. But I think it's a very good question you're asking. LC3 has not been LC is a very good material, but it's not shown yet evidence base for some of the materials, the chlorides and all that. So at the moment we had to use, but my advice is LC3 can be used for personally, but our work is showing that LC3 can be used like a normal concrete covers and all that for the even where we use a bit more cover to the reinforcement, as we know, in coastal or marine environments. And what we are doing now for ordinary concrete, we don't need to change for the LC3. That's our initial work is showing. But rightly, you have pointed out we need to do a bit more work to get that evidence base. LC3 is very early stages, and I hope it will come to the industry here one day. But it's early in Australia as well, of course, the other countries. So it'll slowly get into the system. But it's a good question, Chamodi. It is not for me to answer. Someone is asking, do you provide a CPD certificate for this webinar? I'm sure that.
No, we do not. We do not. We do not. Okay.
So then okay, thank you very much for the very kind comments, Aruni. Thank you on very impressive, saying that very impressive descriptive presentation. Thank you for that. And then so
I think,
Professor,
you can conclude the session now.
Yes. We can conclude the session.
Yeah, there are many other questions, but I think how about if we take those questions and maybe whether they can email to someone if there are any other questions to answer. There are a few other questions. I may take more time. You're right. Yes.
Yeah. Okay.
So, but I'm sorry about not answering all the questions. But thank you. I'm really happy that there are many questions and that I know we have a limited time, and so for very good questions as well. And thank you very much. Finally, thanking the CCI, Architect Jayantha Pereira, and the CCI. I was talking to Mr. Lal the other day. Mr. Lal also, we had a good discussion, and the CCI group for really taking this initiative. One of the first two, of course, in Sri Lanka to take this initiative to really introduce to the construction industry, to start thinking about we need to move into the, I know there's a lot of influence from CCI to the construction industry. So we are in the right direction, and congratulations to the CCI. And thank you for inviting me.
Thank you, Professor Priyan Mendis, for this informative and lots of knowledge, and you went across a wide spectrum. Anybody who's not interested in concrete also gets interested. And this initiative for sustainable construction and green energy is an initiative by the HWK, a German crafts chamber who is partnering with us, and Architect Jayantha Pereira, chairman of the Green Building Council, and of course our president of the construction chamber, got together in running this. So in the future, in the next 3 months also, there will be 3 webinars on the 3rd Wednesday of each month on similar sustainable construction and green energy issues. Kindly keep a lookout, and we will ask you to register with us. And we are also preparing YouTube videos on these, which we will in time inform you all about them. Thank you very much once again, Professor Mendis, and for all the participants who are very interested in this field. Thank you very much.
Thank you.
Thank you, Professor. Thank you so much.
Thank you.
Thank you.